We start by examining the core backpropagation algorithm, the characteristics that define it, and the inherent limitations it carries. Then we'll spend significant time on optimization, the critical stopping criteria, and advanced solutions like momentum, dropout, regularization, and of course, the indispensable atom optimizer.
And after all that, we make the hard pivot.
Right, into natural language processing. We'll contrast the historical approach of n-grams with the revolutionary leap provided by modern word embeddings and the crucial softmax function. So we begin with backpropagation. What are the 6, let's say, non-negotiable operational characteristics that define its scope?
Right. These characteristics, they really define the environment where backpropagation operates, and understanding them explains why it's so widely adopted, even with its flaws. So first, the input values. They have to be flexible, any real values. Modern AI handles everything from pixel intensities and images, 0 to 255, to complex structured data represented by floating point numbers. If the input required rigid binary values, the application space would just shrink dramatically.
And once that real valued input goes through the network, what defines the output side?
Well, that's the second characteristic. The target function output is equally flexible. The output doesn't have to be a simple yes or no.
It can be more nuanced.
Far more. It can be discrete, so classifying something into one of 5 categories. It can be real valued, predicting a continuous price or temperature. Or it can even be vector valued, generating a sequence of words or an entirely new image. This versatility is its real strength.
That input and output flexibility is huge. But the real world is messy. Data is often faulty, incomplete, or labeled incorrectly.
And that brings us to the third point. Backpropagation tolerates noise. Training examples can have errors or inconsistencies, but because the algorithm relies on these tiny iterative adjustments across a massive dataset, is robust enough to learn a generalized function despite those imperfections.
Which is a huge practical advantage over older, more rigid learning algorithms.
A critical one, yes.
Speaking of iteration, let's address the process itself. It's kind of infamous for being hungry for time and computing power.
Indeed. And that's the fourth point. It's a structural reality. Backpropagation is iterative, and it often requires many iterations, many epochs, to converge to a good approximation of the target function. It's an exercise in patience.
But there's a trade-off, right?
There is. This is counterbalanced by the fifth and sixth points. Fifth, interpretability is not a concern. The focus is purely on performance. The ability for us, for humans, to understand exactly how the learned function arrived at its answer is secondary.
So we prioritize predictive accuracy over transparent reasoning. The whole black box idea.
That's the one. And the final characteristic, number 6, it balances out that slow training process. Fast evaluation of the learned target function is usually required once training is complete. The hours or days spent in training are justified because the resulting model, once it's deployed, has to execute its prediction or classification almost instantaneously.
So it's that trade-off again. Slow to learn, fast to deploy.
Fundamental to modern AI systems.
Let's briefly revisit the core mechanism that underpins this whole process, the calculation of error influence using what's called the delta rule. We need to understand how the network determines how wrong it was and then how it distributes that blame backward through the layers.
Right. The mechanism is all about calculating the error influence, or delta, for each node, and then using that delta to update the weights. For the nodes in the very last layer, the output layer, the calculation is pretty straightforward. The error influence is derived directly from the difference between the target output and the actual output, and then it's scaled by the derivative of the activation function. If the network was wildly wrong, the delta is large. Simple as that.
But the hidden layer nodes, the ones in the middle, they don't have a specific target output to compare against. They just contribute to that final error. So how does that work?
That's the conceptual genius of backpropagation. For hidden nodes, the delta, let's call it delta J, is calculated indirectly. It's derived from the downstream error.
From the errors further down the line.
Exactly. You take the derivative of the hidden node's own activation function, and you multiply it by the sum of the products of all the weights and error influences of the nodes they connect to in the layer after them. You are literally distributing the final output error backward, and you're doing it proportionally to the strength of the connection, which is the weight.
So the delta value determines how much a node should change, and the learning rate, which is eta, determines how fast that change actually happens. The weight update, WJK, is the current weight plus that term eta times delta k times xj.
Correct. That eta term is the magnitude multiplier. It's the step size you take based on the calculated blame. And it's a tiny piece of math with enormous implications, which leads us directly into our next problem.
The learning rate, eta, it's often the first hyperparameter a new engineer plays with. It seems simple, a multiplier, between 0 and 1, but selecting the optimal value is notoriously tricky. Why is it such a headache in practice?
It's tricky because the optimal value is just not universal. It is highly dependent on the specific problem, the shape of the error surface for that particular data set, and the architecture of the neural network itself.
Yeah.
There's no formula that dictates the perfect eta.
So what's the standard approach?
The standard and often frustrating approach is experimental. It's trial and error. You're testing values across multiple orders of magnitude 0.1, 0.01, 0.001, and so on.
I tried a learning rate of 1.0 on a complex image dataset once, and my network performance went from just bad to completely nonsensical overnight. Why did that explosive failure happen? And what are the two core opposing constraints that make finding that sweet spot so delicate?
That failure is a perfect illustration of those opposing constraints. You step too hard on the gas, or to use a better metaphor, imagine you are a blindfolded hiker trying to find the lowest point in a vast bumpy valley.
Okay.
Constraint number 1. If a learning rate, eta, is too small, say 0.00001, you are taking microscopic, cautious steps. Convergence takes an excessively long time. You might never even reach the error minimum in a useful time frame. You could run out of your computational budget before you can get close to the bottom.
And constraint number 2, the failure you just experienced.
If eta is too large, like your 1.0 example, you're taking massive leaps. The weight updates overshoot the minimum completely. Instead of settling into the lowest point of the error function, the weight adjustments just bounce back and forth across the valley walls. This causes the weights to diverge, and that results in the nonsensical exploding loss you observed.
So finding the optimal learning rate is just balancing the risk of painfully slow progress against the risk of catastrophic divergence.
That's the game.
That provides great context for why we need more sophisticated optimizers than just basic gradient descent. But before we get there, let's talk about activation functions. These functions introduce nonlinearity, which allows the network to learn complex relationships. What are the key considerations for selecting them, particularly when it comes to computational efficiency?
The activation function defines the output of a neuron given its weighted inputs. For efficiency, early models moved away from the simple step function of the perceptron to the standard sigmoid function,
which gives you that smooth S-curve.
Right? A smooth, nonlinear curve between 0 and 1. And that smoothness is crucial because we need a continuous differentiable function to calculate the gradient during backpropagation. You can't take the derivative of a hard step. An antisymmetric function is one that satisfies the condition f of minus x equals minus f of x. The classic example is the hyperbolic tangent, or tan. The benefit of using an antisymmetric function, which typically ranges from minus 1 to 1, is that it centers the input to the next layer around 0.
And why is that centering helpful?
That centering helps the gradient descent algorithm by making the convergence path more efficient. It's less prone to zigzagging. It just makes for a cleaner optimization process.
That makes sense. But what if we need the output to be continuous? Not clamps between minus 1 and 1 or 0 and 1. What do we do then?
Good question. If you are dealing with a regression task where you need to predict a continuous real value, like temperature or the price of a stock, using a sigmoidal function at the output layer is counterproductive. It limits your output.
So you need something else.
In those cases, the appropriate choice is often a simple linear activation function, where f of x equals x. This allows the network's final output to span the entire range of real numbers, which matches the required output domain. The key, as always, is matching the functional tool to the job at hand.
Here's where it gets really interesting. We've got the engine running, we set the throttle, but how do we know when we've arrived at the optimal solution? If training is too short, we underfit. The model is too simple. If it's too long, we overfit. It just memorizes the training data. We need a precise mathematical way to declare the training done.
Yes, we need rigorous termination criteria, and we can categorize them from the incredibly unsophisticated to the essential mathematical requirements.
Let's quickly dismiss the crude approach first.
The crude stop is simply specifying a fixed number of epochs. You just say, run for 100 loops and then stop.
Which is easy.
It's fast to implement, but it gives you zero guarantee of efficiency or quality. You might stop just before finding a much better minimum, or you might stop long after you started overfitting. It's an administrative stop, not an intelligence-driven one.
So we move to the mathematically sound criteria, which focus on the state of the weight vector itself, the vector w.
Right. We know that at a minimum of the error surface, let's call it ρ star, the error surface must be flat. Mathematically, this means the gradient vector, enabler E of w, must be 0. The gradient vector is a collection of all the partial derivatives of the error function with respect to every single weight.
But how do we use that in practice if we can't exactly hit 0?
We use the gradient-based criteria. We declare convergence when the magnitude of that gradient vector reaches a sufficiently small gradient threshold. The magnitude is measured using the Euclidean norm, which you can think of it as the overall length of the gradient vector.
So if the vector is short, the slope is shallow.
Exactly. If the Euclidean norm of the gradient vector is approaching 0, it means the system is barely learning anything new. It's a strong indicator that it has settled into a minimum.
That makes perfect sense. The learning naturally slows down as you approach flatness. What is the alternative, the one that focuses on the error value itself?
That's the cost function-based criteria. This focuses on the idea that at a minimum, the cost function is stationary. It's not necessarily 0, but it's not changing much. Convergence is declared when the absolute rate of change in the average squared error per epoch is sufficiently small.
Can you give us a sense of what sufficiently small means in a real system?
Typically, this rate of change is considered small enough if it's consistently between, say, 0.1 and 0.01 change in the error measure per epoch. If you run 10 epochs and the error measure only dropped by 0.05 over that entire time,
You've probably hit a plateau.
you've likely hit stagnation, which is often a strong signal to stop.
Now, let's tie this to the practical implementation that prevents us from overfitting, which is known as early stopping. This is essential in modern frameworks.
Early stopping is the disciplined approach. It dictates that even if you set your network to run for, say, 10,000 epochs, you must monitor its performance on unseen validation data. You terminate training when the model's performance on that validation set stops improving.
Even if the training loss is still going down?
That's the critical part. Even if the training loss continues to fall, this is the safeguard against memorization.
So how do you set this up in a framework like Keras?
To configure early stopping, you need to define 3 things. First, the measure. What are you monitoring? Usually it's the validation loss or validation accuracy. We want loss to decrease or accuracy to increase.
Okay, what's second?
Second is the sensitivity, sometimes called min delta. This is the minimum amount of change required to count as an actual improvement. If the loss decreases by a tiny fraction, that might just be noise. You need a significant drop, say 0.001, to count it as real progress.
And the third piece is patience.
Yes, patience. This is a critical hyperparameter. It defines the number of iterations, or epochs, you are prepared to wait without seeing an improvement that exceeds that sensitivity threshold before you terminate the training process.
So if you set patience to 20,
the system will wait 20 epochs for a meaningful drop in validation loss. If none occurs, it reverts to the best model it found so far and then stops.
Patience is key. It ensures we don't stop prematurely because of a small temporary plateau, but it also stops us before we waste time endlessly optimizing a loss function that has no bearing on generalizing to new data.
Precisely.
So we've established the elegance of backpropagation, but its simplicity comes with 2 structural liabilities. What are the 2 major disadvantages we're constantly fighting against?
First, as we noted, it can be slow and inefficient, especially on large, deep networks. This is what drives the need for better optimization algorithms. And second, and this is the classic problem, gradient descent can easily get stuck in local minima. The algorithm only uses local information, the steepness right where it is. So if the initial randomly set weights guide it into a suboptimal valley, it may never escape to find the true global minimum.
That initial weight configuration determines the final performance, which seems like a terrifying lack of control. Let's look at the solutions developed to overcome these pitfalls, starting with momentum.
Momentum is a really intuitive fix to both problems, both the slowness and the local minima. If you think about the gradient descent path as a ball rolling down a bumpy hill, basic gradient descent stops whenever that ball hits a slight dip. Momentum gives that ball inertia.
So it keeps it rolling?
Keeps it rolling. Mathematically, momentum works by adding a percentage alpha of the last movement, delta W at time 2 minus 1, to the current weight update. The current direction of movement isn't just based on the steepness right now, but also on where the algorithm has been consistently moving.
So if the gradients are all pointing in the same general direction,
Momentum builds up and it amplifies the movement.
so it helps us power through those tiny speed bumps that might trick the system into thinking it found a minimum.
Exactly. It uses that accumulated historical velocity to navigate over small, shallow bumps in the error function, which often allows it to find a deeper minimum in significantly fewer steps. The momentum term, alpha, is typically a number like 0.9, representing a strong historical influence.
But there's a catch, right?
There is. The crucial caveat is that momentum, while it's vastly superior to basic gradient descent, still does not guarantee a global minimum. It just improves the odds and the speed of finding a better local solution.
Momentum was a huge breakthrough, but it was replaced as the modern gold standard by atom. Why did atom adaptive moment estimation become the default choice? And what makes it truly adaptive compared to traditional momentum?
Atom is superior because it adapts the learning rate for each individual parameter, each weight in the network. It doesn't just apply one global momentum value, and it achieves this by maintaining two moving averages, known as the first moment and the second moment.
Okay, let's break down those moments. What is the first moment estimate doing?
The first moment is an exponentially weighted moving average of the gradient itself. It's similar to traditional momentum. It tracks the average direction of the gradient, or you can think of it as the velocity. This helps us continue moving consistently toward the minimum by passing minor noise.
In the second moment, that's where the real adaptation comes in, right?
That's the key. The second moment is a moving average of the squared gradient. This tracks the magnitude of the gradient for that specific parameter. So if a parameter has historically seen large gradients, it means that parameter is highly sensitive to the error, and atom will reduce its effective learning rate.
In the reverse,
if a parameter has historically seen tiny gradients, atom increases its effective learning rate to speed up its convergence.
so atom is constantly self-tuning the step size for every single weight.
Precisely. It's a tailored learning rate for every weight, and it's dynamically adjusted based on its own training history. Furthermore, atom includes a crucial bias correction mechanism for both of these moment estimates. This is especially necessary early in training when the moving averages are initialized close to zero.
And that's why it works so well out of the box.
It's a major reason why atom is often the first and best optimization algorithm choice, typically using a default learning rate of 0.001.
We've optimized the movement, but now we have to tackle the other great structural flaw, overfitting. The network learns the training data perfectly, but fails spectacularly on new data. The primary tool here is dropout. You mentioned it solves the problem of co-adaptation. Can you unpack that concept for us?
Co-adaptation is a structural weakness where two or more neurons become overly reliant on each other. Imagine two hidden neurons in the same layer both evolved to detect the exact same feature, say, a vertical edge on the left side of an image.
So they're doing the same job.
Right, done, exactly. And if one of those neurons fails or receives slightly noisy input, the entire network fails to detect that feature because its intelligence is redundant and fragile. The network has essentially memorized the training data by creating these tightly coupled feature detectors, making it poor at generalizing.
So how does dropout prevent this tight coupling?
Dropout is a radical, almost reckless solution. During each training step, an additional layer randomly switches off a given percentage of nodes, typically 50% in the hidden layers, by setting their output to zero.
They just die for one step.
They are temporarily deactivated, yes. This forcing function ensures that no single neuron can ever rely on the presence of any other specific neuron. It forces every remaining active neuron to be robust and capable of learning useful features independently.
So the network has to be more resilient.
It has to be. Since the structure of the network is slightly different at every single training step, it cannot form those co-adapted redundant feature pairs. It forces the network to generalize and distribute its learned knowledge across all its parameters more evenly. And this randomization happens in both the forward pass and, critically, the backward propagation steps.
That's such an ingenious, highly chaotic solution. Finally, let's cover regularization, which also combats overfitting by applying a penalty. How do L1 and L2 regularization differ in their mechanism and their effect on the resulting model?
Regularization is a modification to the loss function. We calculate the standard error, and then we add a penalty term based on the size of the weights. The fundamental axiom is that large weights typically correlate with overly complex models that are too tailored to the training data.
So you are financially, or I guess mathematically, penalizing the weights for being too high.
Exactly. Now for the crucial difference between L1 and L2. L2 regularization, that's R2 equals lambda times the sum of wi squared. This penalty is based on the sum of the squares of the weights.
Squaring them really emphasizes the big ones.
It strongly penalizes large weights, forcing them to become smaller and more evenly distributed. It creates a stable, well-generalized model, but it rarely forces any weight exactly to zero.
And L1.
L1 regularization R1 equals lambda times the sum of the absolute value of wi. This penalty is based on the sum of the absolute values of the weights. L1 has a unique property. It encourages sparsity. It drives many less important weights precisely to zero.
Why would we want weights exactly at zero?
Because L1 acts as a built-in feature selector. If a feature input or the output of a hidden node isn't truly critical, L1 regularization will eliminate its corresponding weight entirely. It effectively simplifies the model architecture and makes it easier to interpret which inputs are truly driving the prediction.
I see. So if you need interpretability or you know that only a subset of your features matter, L1 is preferred.
That's right. And if you prioritize maximum generalization and stability, L2 is often the better choice. In both cases, the parameter lambda determines how fiercely we impose that complexity penalty.
We've built the engine, tuned the throttle, and engineered the safeguards. We have a stable, powerful, mathematical machine. Now let's apply this optimized system to the great, unstructured chaos of human communication. The transition from the mathematics of optimization to the fuzziness of language can be jarring.
It is, but it's the logical next step. Neural networks are simply function approximators. Their performance depends entirely on how well we represent the input data. We're moving from predictable numerical data to symbols, intent, and meaning.
What is the grand ideal goal of natural language processing, and why is it categorized as such a profoundly difficult task for a machine to solve?
The ideal goal is to enable seamless human-computer interaction using natural language. This involves more than just recognizing words. It means developing software capable of understanding the intent and the information expressed in human language, whether it's spoken or written, to achieve specific tasks. NLP is a foundational subdomain, integrating AI and linguistics.
And you mentioned that understanding natural language is challenging for several deep, almost philosophical reasons.
That's right. First and foremost, there are inherent ambiguities at nearly every level. You have lexical ambiguity, a word like bank having multiple meanings. You have syntactic ambiguity, how a sentence structure can be parsed differently. And referential ambiguity, who he or she refers to 3 sentences back. Language is just inherently contextual.
And there's more to it than just the words themselves.
Secondly, yes, language requires massive amounts of general knowledge. If I say, the cake didn't fit in the oven because it was too small, a human instantly knows it refers to the oven.
Right.
But if I say the cake didn't fit in the oven because it was too large, it refers to the cake. A computer, absent general knowledge about the size of cakes and ovens, cannot solve that. Modeling language is considered AI complete. This is the highest tier of difficulty in AI research. It means that to truly solve the problem of robust, generalized natural language understanding, you must first solve the problem of general artificial intelligence itself. You need a system that can reason, store, and utilize common sense about the world.
So, solving NLP requires drawing from multiple domains. It's the ultimate academic collaboration.
Absolutely. We rely on the core algorithms of AI and machine learning, the stable neural networks we just discussed. We rely on linguistics to structure how language is represented and parsed, morphology, syntax, semantics. And increasingly, we draw from social sciences and humanities to understand how language is actually used, the pragmatics, the cultural context, the social dimensions that define meaning and use.
Before deep learning provided us with a way to handle this ambiguity, how did systems try to solve the foundational task of language modeling?
Language modeling is the crucial first step. It is simply the task of assigning probabilities to sequences of words, or predicting what word comes next in a string. It's a probabilistic generative model of text.
And we use this every single day. Autocomplete predictive search suggestions, that's all driven by language models.
Exactly. Formally, given a sequence of words W1 through Wn, the model computes the probability distribution of the next word, P of Wn plus 1, across the entire vocabulary V. The challenge has always been how to effectively model the dependence of that next word on all the prior words.
And the initial solution to that was the n-gram language model.
N-grams are conceptually pretty straightforward. An n-gram is a chunk of n consecutive words. The model estimates the probability of seeing that chunk. But because the history of a sentence could be infinitely long, the n-gram approach relies entirely on a simplification known as the Markov assumption.
The markup assumption is sort of the Achilles heel of this approach, but it's also what made it computationally possible in the first place.
It's the necessary evil. The Markov assumption states that the probability of a word is dependent only on the immediately preceding n-1 words. So if we use trigrams where n equals 3, the probability of the current word is only based on the two preceding words. Everything that happened before those two words is discarded or compressed to zero relevance.
So the n-Gehring size, n, defines the fixed context window. If the dependency is 5 words back, a trigram model will miss it entirely.
Precisely. And the way these conditional probabilities are estimated is purely empirical. Maximum likelihood estimates, or MLEs, derive from counting word sequences in a massive text corpus. To get the probability of xi given the two words before it, you simply divide the count of that full trigram by the count of the preceding bitagram. The model is, in essence, a massive table of historical word counts.
The n-Theorem approach provided some initial success, but it ultimately hit structural limits that really halted progress in NLP until the deep learning revolution. What were the fundamental problems rooted in scale and sparsity?
The core limitation is twofold, and it's all about sparsity. While increasing n, the size of the context window, generally improves performance, the space of possible sequences grows exponentially.
So there are just too many possibilities.
Way too many. The problem of data sparsity means that most higher order n-grams, say 5 grams or 6 grams, are never observed in the training data, even if you train on billions of words. If the model has never seen the sequence the dark chocolate chip cookie and you're using a 5-gram model, that probability is 0.
And if the probability of seeing a sequence is 0, you can't calculate the joint probability of the sentence, and the entire model breaks down. This is the dreaded sampling zeros issue.
It is. The rigidity of the n-gram model means it lacks any form of generalization. If it encounters a slightly different but semantically identical sequence, say swapping dark chocolate for bittersweet cocoa, the n-gram model treats this as an entirely new, unseen event with 0 probability. It cannot recognize the underlying similarity.
So what did they do to fix that?
To handle these unobserved sequences, practitioners had to introduce complex, imperfect techniques like smoothing, which is borrowing probability mass from observed sequences, and backoff, which is falling back to a lower order n-gram if the higher one isn't found.
And the second major failure point was the sheer computational cost required to maintain those count tables.
The cost was astronomical. To achieve reasonable performance, you needed to train on enormous corpora billions of words just to estimate common sequence probabilities accurately. Storing the massive, sparse tables of conditional probabilities for all those n-grams entailed crushing memory requirements. The n-gram model was a victim of the curse of dimensionality, in a sense. The data space was too large and sparse for the model to handle similarity. It treated every word as an arbitrary atomic symbol, incapable of connecting words that appeared in similar functional contexts.
This inability to recognize similarity is the conceptual chasm that the neural language models were designed to bridge. How do they fundamentally solve the n-gram problem and overcome this curse of dimensionality by incorporating similarity?
They transform language representation. They move it from a discrete high-dimensional space into a dense, continuous, low-dimensional space. The key is that neural models allow words to share statistical strength.
What do you mean by share statistical strength?
Unlike n-grams, which see dog and canine as entirely distinct, unrelated indices in a vocabulary table, neural models, through word embedding, can recognize that these two words are similar. And they're similar because they appear in similar contexts, like the word ran quickly. If the model learns a feature associated with dog in a specific sentence structure, it can instantly generalize that knowledge to canine because their vector representations are close together.
This is a major breakthrough because it enables generalization. So let's talk about the process of word-to-vec training. How do we map a word from its sparse, rigid, high-dimensional form to its dense, flexible, low-dimensional vector?
We start with the raw input words, which are often represented as a one-hot vector. If your vocabulary has 50,000 words, the vector for the word apple is 50,000 dimensions long, with a 1 in, say, the 3,214th spot, and a zeros everywhere else. It's massive and sparse.
Okay.
Word-to-vec training involves a shallow neural network, like a simplified autoencoder or models like Skipgram or CBOW, that is trained on a massive corpus to predict the context of a word, or the word given its context. The critical result of this training is the embedding layer. This layer maps that huge one-hot input vector to a much smaller, dense vector, typically 200 to 300 dimensions.
And that smaller vector is the word embedding.
That smaller, dense vector is the word embedding. The values within that vector are no longer just binary counts. They are real numbers that encode meaning based on observed usage.
So what does this density mean? How does embedding actually capture deep semantic meaning, where engrams only captured surface syntax?
Let's visualize the two spaces again. In the original space, that one hot space, words are just discrete symbols. If you calculate the mathematical distance between king and queen and the distance between king and banana, they are mathematically identical. There's no relationship. Every word is an isolated point.
Right.
Now look at the embedding space. Because the embedding function places words that frequently appear in similar contexts close to each other, the spatial relationships become meaningful. Words cluster. All the animals are in one region, all the verbs of motion are in another. This is where meaning, derived purely from the statistical properties of usage, is mathematically encoded.
So the proximity in the embedding space is a direct, quantifiable proxy for semantic proximity in human language. What is the formal definition of this embedding tool?
A word embedding E is a parameterized function that maps words from the vocabulary space V into a high-dimensional, real-valued vector space R to the D. It is usually implemented as a lookup table matrix, theta. Each row of this matrix, theta I, holds the specific vector representation for word Wi.
So E theta of Wi equals theta I.
Exactly. Why is the creation of this specific real-valued vector space so fundamentally important for the neural network itself? Because the neural network is a mathematical function. It requires continuous, real-valued inputs and outputs. Since natural language doesn't natively exist in this format, the embedding function serves as the necessary translation layer. By creating a continuous space where similar words are close, the neural network gains the ability to generalize.
There's that word again. Generalize.
Right. If the network learns to handle puppy in a certain context, the proximity of dog in the vector space means it will automatically apply that learning to dog, even if it has never seen that exact sentence configuration before. This generalization ability is what unleashes the power of deep learning on text data.
And the most compelling proof of this semantic structure is what happens when we use visualization techniques on these vectors.
Indeed. We use techniques like TSNE, which is a powerful algorithm for taking high-dimensional data, like our 300-dimension vectors, and plotting them in 2 or 3 dimensions while trying to preserve the structure. When you visualize a large vocabulary, you see these clusters of related words, all the types of food grouped together, all the capital cities grouped together. This is absolute confirmation that the model has learned meaningful semantic relationships based purely on textual co-occurrence.
This brings us to the output of our language model. The network's final layer processes all these dense vectors and produces a final, raw output vector, a sequence of real numbers. But our goal is discrete. We need to select the single, most probable next word from a finite vocabulary of, say, 50,000 words. How does the system make the jump from that raw vector of arbitrary real numbers to a rigorous probability distribution?
The softmax function is the crucial mathematical bridge. It generalizes the logistic function, and it converts any arbitrary vector of real numbers into a probability distribution where all the values are positive and they sum exactly to 1. It is mandatory for any classification task where the output must be one of k-mutually exclusive classes.
Okay, walk us through those 3 critical steps: the inner product, the exponentiation, and the normalization.
First, the system calculates the inner product of the network's final output and the vector representation of every possible word in the vocabulary. This gives us a raw score, or logit, for each potential word. A higher logit means the network thinks that word is a better fit.
And then step 2.
Second, we apply exponentiation. We're raising e to the power of that logit score. This step is essential because it enforces 2 conditions. It ensures that all the resulting values are strictly positive, and it exaggerates the differences between the scores. The word the network was most confident about suddenly has a score that is exponentially higher than the others.
That emphasis on the higher scores makes the final selection cleaner.
Exactly. And finally, the normalization step. We take the exponentiated score for a specific word, and we divide it by the sum of the exponentiated scores of all possible words in the vocabulary. This division scales the values so they precisely represent probabilities, guaranteeing that the likelihoods of all possible next words sum up to 1.
So when the network processes the context, summer is hot, winter is had, it doesn't just guess the next word. Softmax generates a full probability distribution, assigning, say, 70% likelihood to cold, 15% to freezing, 5% to snow, and then vanishingly small probabilities to aardvark, or bicycle.
That's precisely right. Softmax provides a mathematically sound way to interpret the network's confidence, ensuring the model chooses the highest probability word, the best prediction, while also maintaining a true probabilistic view of all other options, which is often crucial for tests like sampling and generation.
That was an incredible synthesis of deeply technical fields. We've established the essential toolkit for making neural networks stable and efficient, understanding the constraints of backpropagation, the necessity of early stopping, and the power of adaptive techniques like Atom and the generalizing force of dropout.
And we leverage that stability to tackle language. We move from the rigid Markov constrained world of n-grams, which failed because of sparsity and a lack of generalization, to the semantic revolution of word embeddings. These dense vectors allow the AI engine to operate in a continuous space, recognizing similarity and context dependency.
The concept of history compression is a huge takeaway here. N-grams approximate history with a fixed window of n words. Recurrent models, the architectures that use these embeddings, attempt to compress unbounded history into a fixed size vector.
That compression is powerful, but it's not perfect. Our sources make it clear that early recurrent neural networks, RNNs, that rely on simple fixed vectors are hard to learn. They often fail to discover long-range dependencies, like the subject of a verb that appeared 20 words earlier.
And they're computationally expensive.
Very. And computationally, increasing the memory capacity of that fixed vector increases the complexity and memory requirements quadratically. That constraint is precisely why the field is constantly moving toward more scalable, attention-based architectures.
So what does this all mean for you, the learner?
We've seen that the magic of word embeddings is their ability to encode sophisticated, almost analogical relationships into a vector space. The proximity of vectors is based purely on the frequency and context of word usage within massive training corpora. When you look at visualizations where vectors for king and queen are close, and the difference vector between man and woman is consistent across multiple pairs, it confirms the system has learned highly sophisticated structural relationships. And this leads to our final thought. If the system achieves this near-perfect mathematical fidelity by learning relationships purely from billions of words of human text literature, web scrapes, news archives, and if that massive body of source text inherently contains human biases, gender roles, cultural stereotypes, racial slights, how profoundly do these mathematically perfect context-derived embeddings reflect and propagate those human biases? The embedding space is a perfect mirror of the language it was training on. Understanding that mathematical perfection doesn't equate to ethical neutrality is a concept worth deep consideration as these systems become more and more integrated into our world.